There are four types of transformations you can see on a quadratic function. The leading coefficient a tells you whether the graph opens up or down based on the sign. The number value also tells you whether there's a stretch or a shrink. The number inside the parentheses with x tells you a horizontal shift, and the number at the end of the equation gives you the vertical shift. Because the leading coefficient is negative, there's a reflection in the x-axis. And because the number value is 2, there is a stretch by 2. The number inside the parentheses moves the graph side to side. This one is moved to the left 3 units. The number at the end gives you your vertical shift, down 7. Knowing that the functions with negative leading coefficients have reflections, let's find all of those now. Next, let's identify the functions that have a stretch or shrink. Any one that has a leading coefficient greater than 1 has a stretch, and between 0 and 1 has a shrink. The number inside creates a horizontal shift, and the number at the end of the equation creates a vertical shift. Now we're ready to describe the transformations on each function. Number 2 has a stretch by a factor of 3, a horizontal shift to the right 1, and a vertical shift up 2. Number 3 has a reflection in the x-axis, a stretch by 4, and a horizontal shift to the right 2 units. Finally, number 4 has a reflection, and it's moved up 3. The function in number 5 has a reflection, a stretch by 2, a horizontal shift to the left 1, and a vertical shift down 4. This means that the vertex of the function will be -1, -4, and the equation of the axis of symmetry is x equals -1. After we plot the vertex, we'll look at the reflection and the stretch to determine how to complete the graph. Because of the negative, the graph will open downward, and because of the 2 leading coefficient, it will have a stretch by a factor of 2. This means that the y values will grow twice as fast as usual. So as we move to the right 1 from the vertex, we'll go down 2 units instead of the usual 1. The next move in the pattern is 2, 4, but 4 times 2 is 8, and that doesn't fit on our graph. Number 6 has a stretch by a factor of 3, a horizontal shift to the right 2 units, and a vertical shift down 5. The vertex is 2, -5, and the axis of symmetry is x equals 2. This graph opens upward with a stretch by 3. So using our normal parent function pattern, we'll begin plotting the points. But as we move to the right 1, we'll move up 3 units instead of the usual 1. As we move to the right 2, we'll move up 12. Then we'll reflect these points to the other side of the axis of symmetry to complete the graph. Number 7 has a reflection in the x-axis, and it's shifted up 3 units. Because there is no number in the parentheses with x, the x-coordinate of the vertex is 0. After drawing the axis of symmetry at x equals 0 and plotting the vertex, we'll plot the basic parent function pattern, but going downward instead of upward because of the reflection. After we plot the right-hand side, moving to the right 1 and down 1, and then placing our pen back at the vertex, moving to the right 2 and down 4, to the right 3 and down 9, we'll reflect those points to the other side of the axis of symmetry to complete the graph. Number 8 has 2 transformations, a horizontal shift to the left 4, and a vertical shift up 2. The coordinates of the vertex are -4, 2, and the equation of the axis of symmetry is x equals -4. We'll plot a basic parent function pattern from our vertex, moving to the right 1, up 1, to the right 2, and up 4. Then reflect these points across the axis of symmetry to complete the graph. Graphing from standard form takes a bit more work. We'll have to find the axis of symmetry using the formula x equals -b over 2a. We'll substitute the values for a, b, and c into this little equation. That will give us the equation for our axis of symmetry and also the x-coordinate of our vertex. Notice that the value of a is 1, so there's no stretch or shrink for this function. Substituting the opposite of b and a into our formula, we find that the equation for our axis of symmetry is x equals -1. This is also the x-coordinate of our vertex, and we'll substitute this back into the original function to find the y-coordinate that accompanies it. The coordinates of the vertex are -1, 7, and the axis of symmetry is x equals -1. After drawing the axis of symmetry and plotting the vertex, we'll complete a basic parent function pattern. In number 11, a is -2, b is 4, and c is 10. This graph will have a reflection in the x-axis and a stretch by a factor of 2. We'll use opposite b over 2a to find the x-coordinate of the vertex and the axis of symmetry. The equation for our axis of symmetry is x equals 1. Now we're ready to substitute that x value into our original function to find the y-coordinate of the vertex as well. Our vertex at 112 will be just slightly above the top of the graph, but because the graph opens downward and has a stretch by 2, this will allow us to fit several points from our function onto the graph. Applying the stretch and the reflection to our basic parent function pattern, we'll go to the right 1 and down 2, to the right 2 and down 8, to the right 3 and down 18. Number 12 opens upward and has a stretch by 3. We'll substitute the values for b and a into opposite b over 2a to find the equation of the axis of symmetry. We'll plug in x equals -2 to the original function to find the coordinates of the vertex. After that, looking at the pattern for the parent function, all of the y moves will be tripled. To plot the function, we'll move from the vertex to the right 1 unit and up 3, to the right 2 units and up 12, to the right 3 units and up 27. That last point won't fit on our graph. Number 14 is a basic parent function pattern opening downward because the leading coefficient is negative. It does not have a stretch or a shrink. We'll substitute opposite b over 2a to find the axis of symmetry, then substitute the x value into the original function to find the y-coordinate of the vertex. Plot the pattern, going to the right 1 and down 1, to the right 2 and down 4, to the right 3 and down 9. Remember that in standard form, your y-intercept has the coordinates 0, c, so a great way to check your work is to confirm that your graph has the correct y-intercept. In this case, 0, -4. All quadratic functions have a domain from -infinity to +infinity because there's no restriction on an x value we can substitute for a quadratic. The range will be described from the bottom to the top. The bottom of this function goes to -infinity and the top is at +8. The vertex is -4, 8, and because the vertex is at the top of the graph, it represents a maximum point. The maximum value is 8, and this comes from the y-coordinate of the vertex. Remember, we described it as marking your height on the doorway at your grandma's house. The axis of symmetry is x equals -4. Remember, this is a vertical line, and you need to write an equation to represent it. Reading the graph from left to right will determine the intervals of increase and decrease. From -infinity on the left to the midline, or axis of symmetry, the y values of this function are increasing, so the interval of increase is -infinity to -4. From the axis of symmetry to +infinity on the right, the y values of the function are going down, so the interval of decrease is -4 to +infinity. This graph opens upward, so the range from bottom to top will be -6 to +infinity. The coordinates of the vertex are 1, -6, and the equation of the axis of symmetry is x equals 1. Because of symmetry, both ends of the graph will go in the same direction. As x goes towards +infinity on the right, the y values of the graph are going up, and the same on the left, so both ends approach +infinity. The x-intercepts are the points where the graph crosses the x-axis. These x-coordinates are also known as the zeros of the function. The axis of symmetry will help us determine where the graph changes from increasing to decreasing. We'll read the graph from left to right. From the left-hand side of the graph at negative infinity on the x-axis, the y values are going downward or decreasing. So our interval of decrease will be from negative infinity to 1. At the axis of symmetry, the y values for the function begin to increase, and they increase all the way to positive infinity on the right-hand side of the graph. So our interval of increase will be from 1 to positive infinity. Remember that your axis of symmetry is the dividing line between the interval of increase and the interval of decrease, and this comes from the x-coordinate of your vertex. The vertex is at the bottom of the graph here, making it a minimum point, and the minimum value comes from the y-coordinate of your vertex, where the bottom of the graph is located at -6. To convert from vertex to standard form, first you need to expand the binomial squared by using the FOIL or double distributing method. Then you'll combine the like terms and distribute 2. After that, you'll combine the constants at the end of the equation to simplify the function. Use the same process for number 32. Don't be tempted to simply write x squared plus 25. Expand out x plus 5 quantity squared and combine like terms, then simplify. To convert from standard to vertex form, we'll need to identify the vertex. We'll substitute the values for b and a into opposite b over 2a, and then plug that value into the original function to find the x and y coordinates of our vertex. We'll identify the value of a and substitute a and the coordinates of the vertex for h and k into the vertex form of a quadratic function. Remember that the sign inside the parentheses will become opposite because minus negative will change to a plus. Repeat the same process for number 34, using opposite b over 2a to find the x-coordinate of your vertex, substituting it into the original equation to find the y-coordinate of the vertex, and then identifying the value of a as -1. The vertex form of this quadratic function is negative x minus 1 quantity squared plus 9. Now you're ready for your quadratic functions quiz. Good luck!